Hello everyone, today I'll talk about the solution to this problem. I'm not sure what's going on here in the title. I suppose it's all-in-one data structure. The essence of this problem is that we should of course maintain for the strings information about how many times it appears, incremented, decremented, but this get max key and get min key are the most important parts. And everything should work in amortized or average constant time complexity. So this suggests to us that we should create something where there is some linear ordering when it comes to counts. So for instance, count 1, count 3, count 10, count 11. And also those values probably reside within some buckets in our data structure. But this data structure should be able to tell us the maximum and minimum, so a single string from those lists of those with maximum or minimum frequency in constant time. And in particular, since there are some changes, and one change is to create a new string with the count of 1, which is incrementing a string that doesn't exist. That means that, for instance, we can have a string with, let's say, 100 occurrences, and then we keep adding and removing a single string which has only a single occurrence. So for instance, if this was a simple list, we could not just have a list with this thing being 100, this thing, and all those things being from 1 to 99, because then if we add something here at 1, this is the minimum key. If we remove it, then the minimum key jumps all the way up to 100, then goes back to 1, and we cannot go through this prefix every time we want to find that the minimum is 100. Instead, we want some kind of sparse representation. So if we have, let's say, those are the frequencies that are represented, we want to be able to jump immediately from 1 to 3, 10, 11, and so on. Because then we can, if we remember the first and last pointers, immediately look at the most frequent or least frequent values. And of course, what we also need to do, for instance, is to change it to something like this. Because now we decremented some key in this 10, or for instance, we increment one key from those 11s, so there is also now a bucket of size 12, so this connection doesn't appear. And maybe as a result, because there was only a single string in those 11s, now this 11 disappears, so this 10 points to 12. So this is a standard description of a linked list. A doubly linked list, because we need to know when we are at 10, we have a string that has 10 occurrences, we need to get back to 3 so that we can insert a node between 3 and 10. So that is the essential idea. And a doubly linked list is very well suited to solve this, but also we need to know how to, keep all those strings on those lists, to keep some lookup tables, and this is another thing that we'll talk about in my particular approach to solving this problem. The structure that I propose is, at first level, we have, of course, a doubly linked list. So every element has a previous and next pointer. Also, the value, which represents a count, so those are those 3, 9, 10, and so on. And as data, we have a simple Python list that will keep all the strings that fall in the given node. And there is a trick that I learned a long time ago, a very competitive programming flavor of trick, that because most people think that on a simple list, it's impossible to remove an element from the middle of it in constant time. But it's actually possible, and it's possible in constant time, assuming we don't care about the order of elements. I'll show this later in this solution. So this is a nice opportunity to showcase. This is a pretty simple trick, and it's really dirty in general, but for competitive programming it's really in spirit. And so that was the first level. The first level is a linked list of those lists, and we also have some two dummy nodes, a node corresponding to the count of 0 and the count of infinity, which in this problem 1 million will suffice. So there are those two sentinels, so this is a sentinel of head, which points to 1, and 12 will point to tail. That's because we want to be able to easily know that for every real node in the list there exists a previous and next node, and we can insert between them without any problems. So at first the head and tail point to each other, so this is obvious. And we also have two lookup dictionaries, this dictionary points to the particular node of our linked list, the particular list within it, the particular data within it, and the index tells us at which position in this list our value exists. We can keep all of those information in mind easily when running the algorithm. And now, of course, how do we get the minimum and maximum key? Well, the minimum key is in the first node, that's real, so the next node from our head. If that is the tail, of course, there is nothing in our data structure. Otherwise, we return, let's say, the 0th element of that list. Likewise, to get the maximum, we look at the tail, we step back. If stepping back from the tail immediately lands us at head, that means that there are no values, so we return the empty string. Otherwise, we return the 0th string in the corresponding list. Now let's look at some helper methods to remove a key from a list and insert a key to a list. And this is where that trick comes in. So we know that the key, our string, is in the list ls, and it is on the index. We use our lookup table self-index at some position. And now if that position is exactly the last position of the list, we don't have to do anything, we just pop, because pops in constant time the last element of the list. But the problem exists if the index of our element is in the middle of the list, so it's not the last element. So what can we do? Well, we can simply take our element and take the last element, so the data of -1, and swap them with each other. So we swap the element at position ix with the element at position -1, so at the last position. And after that, our element is the last element, and we can pop it. And of course, we have to remember that the element that was the last element on the list is now at the position of ix, so we have to update our index lookup table. Inserting is even easier. It's just inserted in the back, so we remember that its index is the length of the data, and now the length of the data will increase by 1 because we add our key to this list. And also we remember in this count lookup table this list on which it currently exists. And finally, the two functions for incrementing and decrementing a key. So let's start by incrementing. So the two options that we first have to look at is if the key already exists. Well, if the key doesn't exist, then it'll exist with count of 1, and we'll create a new node for it, or maybe add it to the first node. Otherwise, if the key exists, we have to remove it from the list it currently exists at. So we look at that list, we take it from the lookup table, and remember its value for later, because later its value will increase by 1 because we increment the element, we increment the count. And now we remove the element from the list. And the thing that we have to remember to do here is that that list may become empty. So for instance, if we have a single element and we want to increment it, then increment it, then increment it, and so on, we have to remember that we get rid of all those lists. Because at the end we want to have a pointer from head immediately to the current position of the element. We don't want to go through multiple empty lists, because now we won't have constant time for our solution. Okay, so we look, if the list became empty, this was the last element on that list, we have to remove it. How do we remove it? Well, removing is simple. We just look at its previous and next element, and now the previous element points to the next element, the next points back to the previous, so it skips over our current node in the list. We also update our list that we are currently looking at to the previous value, because what we want to do now is to have a node, the node to the left of the position that our new node should be. So it's either head or the previous node from which we removed, so the previous to the list that we removed our element from, or it's simply the list that we removed our element from. So to decrement from 10 to 9, then we would remember this 10. And now the position for our element, we're incrementing, so the position for our element is to the right of this 10. So either the next node in the list is already equal to our v, so we remove it from a list for 10, we add it to the list for 11, and the list for 11 is immediately after 10. We're happy, otherwise we have to create the list for 11s, so we create a new node. The previous and next are the same as, so it's our current list and the next of our current list. Of course, we have to update the previous and next pointers for the nodes. So again, let's say that we increment something from 10, but the next block has count 12. We have to create something like this and remove this link. And this is exactly what we're doing on those lines. And at the end, we just insert the key to the new list, which updates its lookup tables. Now for decrementing, things are very similar. We are guaranteed now that the key already exists, so we don't have to have this if. Again, if the list becomes empty after removal, we have to remove it from our, let's say, blockchain. Now, of course, here, since we want to be on the other direction than when incrementing, because now we're going down in our list, we select the next and not the previous in this case. We decrement the value, and now, if that value becomes 0, we don't have to do anything, but we have to remember to mark that the key no longer exists in the data structure. We can use it by just deleting that key from the dictionary. It's important to remember to do this step. Otherwise, the thing is very similar. If the previous block is the correct block for our value, we're happy. Otherwise, we have to create a new node in between those two values. So again, if we have a 10 and we want to decrement it to a 9, but the previous block is, let's say, a 6, so this is the state, we have to create the state of here being a 9, this 9 pointing to a 6, and to remove this link. And at the end, we insert the key to the list.